All right, so today we're going to do just a quick video on a couple examples of the second part of this solubility rules worksheet. Last we met, we had done a solubility lab that we were able to identify what ionic compounds dissolved in water, which didn't, and that was able to allow us to get the solubility of those compounds in terms of, can it dissolve? Then yes, it's soluble and it's aqueous. Can it not dissolve? Then it is insoluble, and that is what we consider to be a solid or a precipitate right there. And so a step further with this would be to kind of time travel back into when we were going through chemical reactions, and when we were talking about this double replacement reactions. And double replacement reactions, we assumed that at the time all double replacement reactions would occur, but unfortunately, that's not necessarily the case all the time. It's a little bit there's a little bit more that goes into it. So in this case, what we're doing is we're taking these ionic compounds, and we are dealing with ionic compounds. We're assuming that in this chart here that we're performing the double replacement reactions for each of these. And remember, the double replacement reactions are based on switching the positive cation in each of these compounds with the other. So effectively, we're creating two new compounds, two new ionic compounds. And so we have to kind of remember a couple things. We have to remember to balance all charges, and then eventually we will balance the entire equation as a whole. So I'm going to do a couple examples of this, and then you'll be able to kind of fill out the rest. We'll go through some net ionic stuff, and then kind of get out of here. So if I am playing on the big screen right now, I have finally made it. But if not, and of course, if you're just watching this on the iPad, then that of course works too. So in this case, remember we're doing all of these as double replacements. So we'll see how the solubility ties into this here in a second. But let's just practice on creating these compounds. We're not going to balance equations as a whole, but we're going to definitely form new ionic compounds. So it doesn't matter what order the compounds are, as long as the positive cations come first. So in this case, why not do the potassium compound first? And so we're going to have potassium, and its new partner is going to be NO3. Now, because we're creating a new ionic compound, we have to rebalance the ion charges, and we see that it's a 1 and 1, right? Positive 1, negative 1. So that actually works just fine. And then we're going to form our other compound, which in this case, the silver, the Ag, is now partnered with the bromine. And silver is a transition metal, but it always has a positive 1 charge, and our bromine has a negative 1. And so actually these balance out very nicely. So that's where we ended before. But now we're going to go the step further. And now that we know these solubility rules that are on the back of our periodic tables or in your note sheet, we can actually identify which of these two new compounds is our precipitate, our solid, our insoluble product, because that's the only time that these double replacement reactions truly occur. So take a look, and we see that according to our solubility rules, specifically rules 1 and 2, where rule 1 talks about alkali metals and rule 2 talks about nitrates, those are soluble. And so we know that the state of matter of the potassium nitrate product is aqueous. Now we get to the silver bromide, and we say, well, bromides are usually soluble, however, not when they're with silver, and that's rule number 3. And so we know that this is solid. And because of that, I'm going to, you can either circle it as the directions say, or highlight, and just know that silver bromide is now the solid precipitate, or the insoluble product that forms when those two things react, right? Silver nitrate and potassium bromide. So let's do the whole first row, and we're going to just go through. Let's just keep up with the cation from the top row. Let's do that compound first. So the sodium is now going to be with the NO3. Remember, that 3 is a part of the nitrate group, so it stays there. That's not telling me that I have 3 nitrate groups. Sodium's a positive 1. That's an alkali metal. That's a -1 there. Let's look at the other compound that forms. This is silver, and this new partnership is silver and carbonate for silver carbonate. Now, however, we are making our formulas based off of the charges, and remember, when we have these charges, we can just crisscross those values to then make sure that we have the appropriate formula. And then we would balance the entire equation after that. But for this, we see that sodium nitrate, according to our rules, is aqueous. And then for our rules, I believe it's rule 6 for us, that carbonate, that those carbonate compounds, the compounds that contain that CO3, are primarily solid, right? Because they're insoluble. So there is another solid compound, and we can highlight that. Now, again, once you're done with the charges, you can also cross them out if they are getting in the way. Here we have calcium is now going to partner up with nitrate over here. Calcium's a alkaline earth metal, so it's a +2 charge. Nitrate's -1, and so we are going to cross those. And that 3, remember, is a part of the nitrate group, but a 2 goes out there, and that balances out that formula there. And then we have our silver and the sulfur. Silver's +1, sulfur's -2. So I'm actually going to move that sulfide ion over a little bit, and then we're going to put a 2 here where we would need a 2 for the 2 silver. According to our solubility rules, that product is aqueous, that product is solid, and so we yet again have another insoluble product. And the idea behind this is that this means that these reactions will happen, and I'll show you that how it looks the other way here in a little bit. So one final one. Let's keep it up with this. Ammonium is actually our only positive polyatomic cation. And so what we're going to do is that is going to be NH4. It is a +1 charge overall. It's going to partner up with the NO3, the nitrate, and they actually balance each other and complement each other quite nicely. And then we're going to have the silver with the hydroxide group. The silver is a +1, hydroxide's -1. So you see how I have to remember to balance the charges out to make sure I have the correct chemical formulas. According to our rules, ammonium and nitrate, those together are very soluble. And the silver and the hydroxide group here is going to form an insoluble product. It's not always going to be the second product, right? That's just how this worked out, the way that I did it. But there could be instances, and actually I'll just do this one really quick. There could be instances where you do end up with 2 soluble products. And when that's the case, then both products are aqueous, and actually the reaction doesn't happen at all. I X'd out this because that gives you 2 solid products. That won't also happen. So that's why that was just a bad combination there. So don't worry about that one. But in this case, when we have K and Cl, you're going to want to put this 2 here. Don't, because remember, potassium being an alkali metal and chlorine being a halogen, they actually complement each other nicely. We only need 1 of each. Plus barium and bromine. Now, barium's a +2, bromine's a -1. You crisscross. I'm actually going to need 2 bromine there to balance that formula out. According to our solubility rules, we have that aqueous product there, which is our potassium chloride. That's based off of rules 1 and 3. And then we also have barium and bromine. Bromides, according to rule 3, are soluble unless they're with silver, mercury, or lead. In this case, barium is none of those, so this is aqueous as well. So we're not going to highlight anything here, and what we're going to look at is when these both are aqueous, well, what does that mean for the entire interaction as a whole? So this should be a good stopping point to allow you to kind of finish off the rest of those empty boxes there. Remember, you can cross out the one that's over there. So a little bit of review for our double replacement reactions, a little bit of review with our solubility rules, identifying solubility, insoluble or soluble, right, solid or aqueous. And now we're going to go to the note sheet. And so we talked about the solubility rules up here last we met, and now we're going to kind of apply it to this idea of these double replacement reactions. So our double replacement reactions are always going to start with two aqueous reactants. So again, the reactants are aqueous. And then here you are going to use the solubility rules to identify if it is soluble or insoluble. Remember, you will never have two solid products. So if you do that, so you might have read something incorrectly in the rules. And then you could end up with two aqueous products, but we're going to get there in a second. So what happens here, and this is the example where if I have silver nitrate and sodium chloride react together, well, what's going to happen is those two cations on the front are going to switch spaces. They're going to switch partners. That's where we get the double replacement idea. And then we end up with this thing called a complete ionic equation. And so by looking at this, we can define what a complete ionic equation is. And the complete ionic equation is an equation that shows all dissociated, which just means separated. So you can also put separated aqueous ions in solution. And so you could see the difference between the molecular equation here and the complete ionic equation is that anywhere I see an aqueous solution, what I'm doing is I'm actually going to separate it into its individual ions, right? And so silver nitrate is made up of a positive silver and a negative nitrate ion. And so you notice that you do need to incorporate those charges, and you also need to make sure that you note that they still are aqueous even when we separate them. All right, aqueous means that it is able to dissolve. And so anytime we have an aqueous substance, we can separate or dissociate it, if it's an ionic compound, into its individual ions that create it. But what you'll see here is we do end up having an insoluble product, right? A solid form, and which is that silver chloride there. And so what occurs now is, now that we have the complete ionic, what we can do is see which ions are free, which ions exist on both sides of the equations that aren't paired up, that don't have a partner, and we call those spectator ions. So if you think about spectators for sports or concerts, right, those are the fans, those are the people that are watching the shows go on, the sports events go on. So that's what these ions are called. They are ions that do not participate in the reaction. And so in this reaction, when I look at these spectator ions, I like to cross them out. I like to identify them and then cross them out so that I know that they're not really playing a role in anything. And so if I were to look at this equation right up here, or this complete ionic, where I've separated everything out, I'm going to try to see which ions show up on both sides that are by themselves, right? What I see is that there's this nitrate ion there that on both sides, it does not have a partner, as well as this sodium ion, right? But other than that, the other two ions that are on the reactant side over here, right, that's silver and chlorine, that ends up coming together and creating the silver chloride, which brings us to, of course, our net ionic equation, which is taking those ions that actually participate in the reaction and creating our precipitate. So the net ionic equation shows, and let's start it with what the wording that I had before. It's an equation, all right, a chemical equation that shows the ions that participate in the reaction and form an insoluble, right, product. And this is what we call, again, our PPT, or precipitate, right? Our solid precipitate. And so when we have a reaction versus no reaction, a reaction is when a precipitate is formed. Whereas no reaction is when all compounds are aqueous. All right? When all compounds are aqueous, that means that they all completely separate and split up, which means that if we look at something like this, this doesn't form, right? This is the precipitate here based on the example, right? The AgCl is solid. It forms at the bottom. But if we had these ions just floating around with each other, right? The Ag, the Cl, the Cl, right? Well, they would all just cancel each other out. They would all be considered spectators if they were all aqueous, which means that nothing is going to actually happen, all right? So let's take a look at some examples of this. I'll do one for you on the worksheet, and that should be good. So again, I'm trying to make this a little bit shorter. It's not working too well, but hopefully being detailed enough for you to kind of get you started on this. So your equations are basically going to be equations that you write the formulas for. We give them to you in the notes, but you also have to make sure that you balance them, right? Anytime there's no coefficient, it does mean just one. And so we do have to take into account how many of each ion we have exist. So let's write the complete ionic equation here. Again, the complete ionic equation is going to take all of the aqueous substances and split them up into their individual ions and keep the solid insoluble substance together. And so in this complete ionic equation, I have barium, and I'm just going to go in order. Barium is a +2 ion charge. It is aqueous when it's dissolved. So you have to have charge number, and you have to have, or charge in general, and you have to have states of matter on everything. And then here I have chlorine, which is a -1 charge, but I see that I have 2, so I'm going to put a 2 there because I have 2 of them. Right, so just making sure that you're taking into account all of those. Here I have the same thing happen with sodium. Sodium's a +1. There's 2 of them. It's attached to an SO4 group, which is a -2 polyatomic charge. And then on this side, our sodium chloride is made up of sodium and chlorine. But again, you notice that even though there's no 2's down here, I still know I have 2 of those things. So I do have 2 of each ion, and that's because of my balance equation, right? If I have 2 sodium ions on this side, then I have to have 2 sodium ions on that side, so on and so forth. And then, of course, we have our barium sulfate, which is our solid product that sticks together, that does not separate. And so what are the spectator ions? The spectator ions are the ions that are just watching the show happen. They're not doing anything, and so they appear on both sides. I see that a spectator ion is Cl, right? The 2 chloride ions, and the sodium, right? The 2 sodium ions I see on either side. So because I've identified them, let's get rid of them. The chlorines go away. The chloride ions, the sodium ions go away, and now we're left with what's actually going to create our net ionic equation, which is going to create our actual product, which is the barium and the sulfate group that are going to bond together. And that force of attraction is going to create a strong ionic bond that does not dissociate, does not dissolve. It is insoluble, and that is our net ionic equation. Reaction or no reaction? Reaction, right? Check. And that's because of that solid insoluble product. So now let's take a look at just what happens. You see all these are aqueous. And so when I work through this net ionic equation, you also see that they're the same thing on both sides. And it could have been changed either way. But if we were to just write all these out, there's the sodium. Here's the chlorine that it is attached to. Then we have hydrochloric acid, which is a hydrogen ion, and then a chloride ion again. I am just literally going to duplicate this to save time, which if you're on your iPads, I highly recommend doing as well. All right, and so what do you notice? Well, I notice that I see a sodium ion on both sides, so by itself, so that's a spectator. I see a chloride in different places, but I see that chloride is on both sides. That's a spectator. I also see that hydrogen is a spectator, and what do we do with spectators? Well, we cross them out. And everything crosses out. So is there a net ionic equation? No. There's no net ionic equation because there's no product that forms, which means that no reaction occurs. All right? And so when we know that these products are aqueous, then we can just say, hey, that's not going to happen, and then we can not worry about it. All right? So what we're going to do is we're going to take this and we're going to run with it in our next worksheet, which is our net ionic equation writing. And so what we're going to do is I'm going to do this first one as an example, and I'm going to let you kind of work alone or in your small groups or partnered up. And you're just going to try to work through this the best you can, and we'll talk about it next class. And so sodium chloride, and you see how I give you the word formula. So sodium, that's a +1 charge. Chloride is chlorine, so that's -1. This lead, 2, remember 2 doesn't mean that it's Pb2. It means that it is lead with a +2 ion charge. Nitrate, that is an NO3 group that is on the back with a -1 charge. It is going to produce, right, sodium, which is another plus. Again, all the charges are the same. They're just now with different things. All right, and so knowing that, now I can make my formula, or like the note said, molecular equation. So here's sodium chloride. Let me do it here. NaCl, right? The +1, -1. That is aqueous. I do say assume all reactants are aqueous, and that's the only way that these double replacement reactions do work. Pb, NO3, 2 is aqueous. I know that this is the formula because remember, lead is a +2, nitrate's a -1, and I crisscross those charges to then get the correct formula. You need the correct formula to have the right amount of ions to cancel out. And then we have our sodium nitrate, NaNO3, plus lead chloride. This is going to be PbCl2 based on the charges. Now, I do not know what the state of matter of these are yet, so I use my solubility rules here. So I'm going to take this, I'm going to say use solubility rules to then figure out what those are. I have an aqueous product here, I have a solid product here based on those, and now I have to balance the equation as well. I notice that there's 2 nitrates, 2 chlorides, so I'm going to put 2 in front of there, which makes me put a 2 in front of there. So now I'm going to go through anywhere that there's aqueous. I'm going to create my complete ionic equation. I have, when this aqueous one splits up, there it's going to create 2 sodium ions and 2 chloride ions. The 2 because there's a 2 in front. And then I have a lead ion with a +2 charge. That is aqueous. I have 2 nitrate groups, right? That 2 tells me that I have 2 of them. So we put the number based on how many we have in the formula or based on the balanced equation. And then I create another 2 sodium ions because that is aqueous. It splits up. Another 2 nitrate ions. That splits up. And then I create a solid lead to chloride product, right? And so I'm going to cross out all of the spectators. The spectators are the ones that appear on both sides. That would be sodium. that would also be nitrate, right? Those ions do not have partners on either side, so they are just watching this happen. And now I can put on my net ionic equation. I always write the cation first because that's how I write it in the formula. So even though it's looking like Cl in front, I'm going to put Pb with the positive 2 there. I'll just get in the habit of doing that. And of course, I have 2 chloride ions. And the beauty of this is it shows that I have 2 chloride ions for every 1 lead ion there in the formula. So pretty neat there. And so you can see the things that are actually participating in this chemical reaction are the lead and the chlorine to produce that solid. Right? And so we're effectively just trying to figure out, based on at the very beginning, what product is solid. We can figure out which of the ions took place in this reaction to then produce that insoluble solid precipitate. And so that's how I'll have you go through this. Hopefully that helps. And just note that I did make some changes here. If you didn't have these changes, just make sure dichromate, we don't have rules for that. So I just told you that is the precipitate. So this is solid when you go through. So hopefully that helps. Of course, as always, if you have any questions, always reach out. All right. Take care.